But one of the things that we've learned in doing this is that, this is sort of a new data set no one's ever had before. We're looking at it from a different perspective. And it takes, it takes time to learn how to use these data. And you'd think that, sometimes that, that coincidences would be easy with geostationary satellites, and they are to some extent. But at the same time, we do some limb observations, and sometimes, just finding observations or the correct observations with other satellites can be somewhat challenging sometimes. So I will commend the ICON team for having some tools to help you find coincidences, sort of when the observations are occurring. So some of these sorts of tools are very valuable that we found for doing some of this stuff for comparisons. So, these sorts of observations are, just putting everything together, making sense of it. It takes time, and you learn a lot in the process. And that's where, so at the end of this talk, I'll come back a little bit to some of the stuff that where we've made advances as we've gone along, and how we can, we learn to do things better. And certainly, sort of, suggestions or, maybe it's sometimes complaints from the people who are working with the data are very valuable because, we work with the stuff, but sometimes there's some issues in there we don't recognize, and certainly we look for feedback from everybody and who's working with the data. So I just touched on some of the things we've learned. One of the things, at least somewhat surprising in some ways to me and other people, was that how, even for relatively weak geomagnetic disturbances, how these extend down to even low latitudes. Traditionally, people have thought about this as being sort of a high latitude thing about the geomagnetic activity. But what we see in the gold observations is we see this in the temperatures and also in the composition information. That some work that Fazlul Laskar's done and Xu Guangkai have done on these two sets of data. And they've sort of shown, that basically some of these effects extend even to low latitudes for relatively modest conditions, relatively small disturbances, that you can have significant changes in the composition and temperature even at low latitudes. So certainly there's a couple of papers out. Each of them has published papers on these things. You can find these in the literature. So it's really been one of the surprises that we've had in the data. And of course, with geostationary data, a series of observations like this, full disk, learning how to use it, like I say, is a bit of a challenge sometimes. Fazlul has done a lot of work on assimilation. I was just showing some recent stuff here where he's done some basically simulation using simulated data. So it's the first step into actually simulating the actual data. He's done this simulation of actual data on T-disk. Just recently, he's done some tests on ODIN2, and he sees significant improvements in the basically the results from the simulation of the ODIN2 data. Significant reductions in the errors that are with respect to the root mean square errors. So this sort of shows you some of what he's seen. It gets like an 80% reduction in the root mean square errors compared to lower atmosphere only assimilation. And just as a note here, that with just T-disk alone, he found that actual gold data, if he only assimilated it, he found that there was a 23% improvement in the errors in ODIN2. That was actually using just T-disk, using the ODIN2 in gold as a comparison for what the model or the simulation was giving, so he could see that it had an independent measure of what the ODIN2 was versus what the model was giving. It also improved, of course, if you improve ODIN2, you improve TEC and some of the ionospheric densities. He saw that when he assimilated T-disk data. He hasn't gotten all the way through doing the ODIN2 data yet, but you can see that he's getting better improvement even with assimilating ODIN2, which isn't surprising, than what he got just assimilating the T-disk data. Just to remind you that, as I mentioned, gold does some limb observations also. One of the sets of limb observations that gold does is some occultations. And these, of course, are at sort of fixed longitudes on the Earth, either over the Pacific somewhere or over Africa. Now, Katie Greer has done some work with this. I just wanted to concentrate on, for today, on the O2 densities. And sort of it wasn't surprising that the densities in MSIS and some of the other models were a bit off from what we're measuring. You know, because, okay, yeah, we've never had very good measurements of O2 down at 170, 180. You know, you can't get a satellite down there very, you know, basically can't get it at least for any length of time. You basically kept a few rocket data, a few occultation, sets of occultation, solar occultation data. What was surprising, really the more surprising thing though, is sort of like that we see some local time differences versus what the models show. So, of course, O2 densities are important for, you know, sort of where energy gets, how the energy gets deposited in the thermosphere, for basically it's tied into the O chemistry. So these are some important, we're seeing some important differences in this, you know, this is something we haven't done much with. I know Katie's trying to work more with this, or sort of get some, you know, get some support to work on this more, and I think it's a really worthwhile project, and something that's really sort of very surprising in a couple of ways is how far off the densities are, and just that the local time dependence is significantly different than what's in the models. Another place where we had some surprises, it's still a bit of a puzzle, is we're able to do, there have been some eclipses, solar eclipses, and you know, you can do the TI-GSM calculation, just look to see what the composition should be doing, the temperature should be doing. And we've beaten the errors, we've beaten on the errors, we've improved agreement a bit, but we still have some significant disagreements with what the models are calculating, that we are actually seeing significantly more changes in the both parameters. And you know, I always question the temperature. The temperature is a little bit more of a tenuous, a little bit more signal noise isn't quite as good on that. But the Odin 2 was always off significantly. So I've always believed that there was, you know, that it wasn't confident that we were as much off as we were originally saying, but I was always pretty relatively confident that there was an issue there, because we did have good signal to noise in Odin 2. We know how to do that really well, and that wasn't agreeing either. So we see significant disagreements between what we think the composition should be according to the models when we do all the calculations and what we actually observe. So there's, you know, certainly some questions here about, you know, our understanding of what is happening as far as the processes in the thermosphere and ionosphere during such events, and maybe even other times also. I guess the most pleasant surprise was, I guess, the nighttime ionosphere. And I think ICON's been doing a lot of great work on that. Certainly we have, Gold's observations have been really surprisingly good, because we weren't sure how well we would be able to do this. It's been worked out much better than we expected. We do scan just the region near sunset for about a couple hours, basically. I think we occasionally do off to something later local times, but typically it's just near sunset. And we scan most locations multiple times. You've seen some of the stuff at some of the various meetings about mesoscale waves. For example, some of the people in Germany that have done some work on that, some X structures in the ionosphere, equatorial ionization anomaly at night, the crest merging, wave effects, stuff like that. I'll show you a little bit of this, but I don't have time certainly to go into much of this. Just this is, you know, being able to look at it and watch this as it develops over the night, and looking both at the same locations multiple times has been very valuable. I mean, just mentioned one of the things that was sort of, we do see wave effects in the equatorial ionization anomaly. Certainly, we've always, these seem to be connected very closely to what's happening at lower altitudes. You know, this is an earlier paper where you see alternating north and south crest. More recently, Qian has also done some stuff with a 6-day period. So again, both times we're seeing a connection to what's happening in the mesosphere, or at least a correlation with what's happening in the mesosphere. Seems to be connected. that we're seeing these relationships. And I'll sort of get to the end here. I think I'm not sure exactly where I am on time, but I figure there's a lot of stuff I could talk about, but some of the things I think we've learned a lot, but also there's a lot to learn. One of the things, of course, we learned is that keeping the instrument, keeping track of it is a bit of a challenge. I've shown you there's two curves here. Hopefully, it's difficult to see from back. I apologize. I didn't expect to be in such a big room. I was used to these concert sessions where we have a much smaller room, about half this size at best, maybe a third this size. And so there's two curves here. And one of the things we've had is challenges we've had is that there's some degradation in the O2 O2 signals, and we realized pretty a while back, for about a year ago, that a lot of this degradation actually wasn't instrumental. It was actually in our processing, and the dotted lines, vertical lines here, where GEM shifts, and when we had those shifts, we could see that there were some differences before and after that weren't making complete sense. So we went back and did some reworking of this, and this shows there's a flat field correction that we used during the processing that was introducing the error, or at least much of the error. We've approached this a different way, and the blue is the old version, the orange yellow is the new version, and you see that it's much smoother. For example, in the LBH, in the 1356 correction, max 13. Well, one of them is 1356, and the other one is the LBH correction. So it's much smoother in the new version that we're using. So you can see on the bottom that what's currently being used in production, how that varies for LBH, and the orange shows what the new one looks like. So we think these are going to remove some of the biases, and you can see the current version here versus the new, which updated version, which we expect to release hopefully near the end of the summer. So you can see that the curves are much closer. There's still some differences. Some of these are definitely due to geophysical conditions. For example, on that last day there, you see some differences, and it's clear that that's actually some of those differences are due to geophysical stuff. These are on the right here is temperatures. We know that will affect the Odin too. It also affects the temperature slightly because there is a little bit of degradation in the peak values of the LBH, so it makes the band look like it's fatter than it is if we don't correct it properly. So just to sort of show you that, the day by day, and as you can see on that last one, that the day by day, if you look at it every 24 hours, it's actually, there's 2 days before the GEM shift and 3 days after, and it's the second day after the GEM shift on that last one there that you can, well, there we go. Oops, I didn't mean to do that. Well, I just got out of it. Okay, all right, that wasn't what I wanted to do. Anyway, back to this. I was trying to get it up, and I went back to the desktop. So anyway, basically right about there, that's the second day after. You can see that really seem to be some geophysical activity that's the cause of that difference that you see in the LBH temperatures. Okay, so anyway, just wrap up here in summary. It's a lot of unique challenges. Didn't mention very clearly that we'd have done some intercomparison with ICON. That was a very useful exercise. We're trying to get all the Odin to just on a more consistent basis, such that if you look at the two, you don't have big differences. Try to eliminate some of those differences. We're going to do the same thing with, the same thing is planned to do with the GUVI measurements. We have looked at that a little bit, but we have more work to do there. Certainly, we have some puzzles, and the simulation is very valuable, but there's a lot of things that we don't know about why we're seeing some of the things we're seeing. So we've learned that there are some interesting differences where we didn't expect them, but we don't understand those yet. Certainly there's some work to be done there. In the future, I think some of the operations we are learning to do a better job, give some better data products that will help people make even more advances in understanding what the thermosphere and ionosphere are doing. And with that, I will stop and take any questions. Thanks.
Do we have any questions? All right, I have one question. When you were showing the assimilation work, what models are you working with?
Okay, all right. Well, that's the work that was done in assimilation. Fazlul was working with Wacom-X and Dart, using, so basically that was the models he was using. So it's basically, of course, the Dart is, I guess, not a model, but it's a way of assimilating the data. So, there are other models, but which could be used, but that's just what was convenient to use.
Right. Excellent. Oh, yes, please.
I think you're asking why the higher O2 at dawn, for example? Yeah. Okay, I think Fazlul did a paper on that recently. We looked at that, and actually it does seem to be, I forget all the details of that, but I don't know how to best handle this, because I know that we looked at that and sort of reduced, it does seem to be actually some higher O2 densities, there are some differences at dawn versus other times of the day because of the way the flows go. I'll have to, I'll tell you what, I'll get a Fazlul's paper reference for you, because I think he basically had a paper on that recently.
Thank you. Okay, we are ready for our next presentation, I think.
And I think, okay, all right.
Thank you.
All right, I'm told I can advance the slides using, is this it? Okay, great. I'm Rob Pfaff. It's a pleasure to show results from our rocket campaign of last July, 2021, that were 2 rockets flown in conjunction with ICON. And I'm going to tell everyone right now, we don't understand our results, and we certainly need help and ideas. And I brought my pad up here to take notes. Any rocket campaign involves a lot of different people. You can see them here all listed. And in general, you want to tell the whole story, and I just don't have time for that in 15 minutes, but I'm happy to talk to people about this. This was the second of our Dynamo campaigns. It got delayed because of COVID. We launched 2 rockets last July. Now, I'm going to talk about our motivation. This is a rather long outline, but I'll go through it quickly, hopefully. I'm going to talk about why we launched the rockets, the ground-based instruments. I'm going to show some results, of course, talk about the ICON data, and then really at the end say we want to try to understand our results. Now, the Dynamo is sort of depicted here. The northern hemisphere, southern hemisphere currents. Of course, this is daytime currents close. This is the SQ system. Everyone's familiar with this type of plot. Does this also have a pointer? Okay, perfect. So the Dynamo 1 campaign, which took place in 2011 and 2013, had 2 rockets launched into the at noontime, when it was basically a westward current. We published results from one of those in GRL. That was without ICON. We saw sort of a spiral in the winds and a spiral in the currents. We were really quite excited. And so what we did this time was what we wound up doing was launching 2 rockets in the afternoon when the afternoon current was peak. And that's what I'm going to show you today. We like to go back with Dynamo 3 and have two rockets in the morning so we can have sort of all sets and put them all together. And we also want, of course, launch during disturbance Dynamo and all this. There's lots to be done. And if anyone out there is really interested in launching rockets in the Dynamo, there's plenty of room. And it used to be in the 60s, this and the electric jet were key topics. So we really want to continue with that. This, as we all know, the daytime dynamo ground-based magnetic field measurements are what give us really the clues to what's going on. We have the equatorial electric jet is very strong. We have the daytime westward current. In fact, I tell people Wallops is ideally situated to look at that, which it is. And then we have the afternoon current. So what I'm going to talk about today is 2 rockets in the afternoon. Okay, let's see here. Okay, so the structure of our experiment was to take the dynamo equation and try to measure all of the parameters that go into that. The electric field, the winds, the currents, of course, and then this conductivity tensor. You really want to measure everything. You want to measure the atmospheric density and the ion species and all that. We do the best we can. We have to use some models. We measure the plasma density, and so that's what we're trying to solve. Okay, so we know the currents are driven by winds, but as we showed in our Dynamo 1, it's much more complicated. In fact, the winds are much bigger than just sort of the standard tidal theory of 30 meters per second. We saw 150 meters per second, but we also had an electric field going the other way, and that made it look like it was actually very small, driver, but there's lots more going on. So what's going on in the afternoon? So first of all, we put together our experiment that consists of 3 sub-payloads, and we had 2 of these. Had a small spherical payload. We've flown many times. It was developed by Nelson Maynard back in the early 80s, so I call it the Maynard sphere. And that gives us high-quality E-fields and anatometer data. We had our standard payload in the middle with longer booms. Also it was a 2-point measurement of electric fields and currents. We had a magnetometer. We had higher frequencies, interferometry, things like that. And then we had the UNH. This is Jim Clemmons. He had a separate payload right here, and he's going to show you later. He measured winds and had a mass spectrometer and things like that, ionization gauges to get the neutral density. Really tremendous instrument complement right here. Now you might say, why weren't these 2 payloads together? Why did those have to be separate? It wasn't to get a 2-point measurement at all. It was simply that Jim didn't want to spin, and I wanted to spin, and we were kind of going to have to duke it out. And we said, well, why don't we just have 2 payloads? And that meant 2 attitude control systems. But Jim was able to look in the RAM direction the whole time. He'll tell you more about that later. And we were able to spin, which is what we wanted. Okay, so everything folds up inside the skin here when we launch. And here's some pictures of the hardware, just so you can see. Here's the main payload. Here's the spherical payload. Here's Jim's winds, mass spectrometer, neutral density. And the other very important part of our experiment was the ICON satellite. So this was right from the start. We wanted to make sure we launched in conjunction with ICON. And to do that, there's all sorts of predicts, as the ICON team will tell, the ICON orbit, which of course went precessed between northern and southern hemisphere. So we waited till that time of year when it was gathering data in the northern hemisphere over Wallops. And there you can really have good predicts that we got. And Scott England isn't here, but he really took care of this. And so that's essentially what we did. And then we had this is sort of the ICON observations over the longitude of Wallops. And the whole idea here, without going through this, is, this is the local time. This little dotted line is the morning. This little dotted line is the afternoon. Blue means it was looking in the north. Pink, looking in the south. So we wanted, obviously, blue over Wallops at the right time when we had strong currents. And if you've been in this business with the rockets, you just can't be too choosy. So we said we'd like ICON in the vicinity of Wallops, but the main decision-making ground-based information that we used to determine when to push the button was the ground-based currents. I'll show you this in a second. So when the currents were high and ICON was in the vicinity, we launched. Originally, we were going to have one afternoon, one morning. We launched one in the afternoon, and then we had another really interesting afternoon event, so we launched into that, as I will show you in a second. Okay, so in our window, you have to negotiate with Wallops. We had a 2-week window. starting on July 6th. And we launched one on July 7th and one on July 11th. Okay, and those are the actual 2 launches right there. So not exactly with Icon, but they were certainly good enough, as I will show. Okay, so here's all the magnetometer data. This is the magnetometer data from our window starting on July 3rd. And this actually we have from Fredericksburg. We also had our own magnetometer at Wallops. I just don't have the presentation as nice as this, but it's essentially the magnetometer at Wallops and the one at Fredericksburg were essentially the same. And what we did was we launched one rocket there when the afternoon currents were strong, were enhanced but not super strong. And our second one was launched right there. In fact, I went through a lot of angst over whether we should have launched the first one and went ahead because it was a good icon conjunction and we were perfect for the range was green and there were no ships at sea, all that stuff. But actually, I think it's turned out very interesting because we have a sort of a moderate event and a very strong event. And I should really point out that this current is one of the strongest I've ever seen. This is 50 nanotesla at mid-latitudes. So my goodness, this is fantastic, right? So I didn't mention KP or magnetic activity. Which of the 2 do you think had the stronger magnetic activity? And they were both quiet, but really it was the first one that had KP was higher. This one, the second one, was uber quiet. Very low, quiet, quiet, quiet. In fact, I don't know if Bela Fayer is here, but when we were grad students at Cornell, Bela would always say, it's not the quiet day, it's the quiet, quiet day. The whole atmosphere has been quiet for a long time. We get these big swirls or whatever. So anyhow, here we have this data set where we have 2 events and 2 rocket launches, one in moderate and one in strong. So how can we explain what's going on? Here they are just on top of each other. I'm going to have to go a little quickly here. Those are the same components. I think that was the Goddard mag, by the way. So Yosuke Yamasaki, who I hope is here in the audience, provided the models for these 2 events using the ground-based. Remember, this is a global current system. It's not just something that happened at Wallops. So we want to look at the global patterns. And Yosuke-san did that here. This is the first event. And the red is the actual measurements from the ground. And this is the second event. So you can see the whole daytime dynamo was very enhanced on the second day, the day that was quiet, quiet. Okay, so now we had our Terry Bullitt's Viper data from Wallops. Without spending a lot of time on this, is the first launch. The second launch we launched at 18 UT, which was 2 p.m. Rather benign ionosphere, no huge sporadic E or anything. Here's actual traces for these 2 times. At the second event, there was sort of more going on, but it wasn't like it was, the ionosphere was upside down or anything. Okay, so we launched our 2 rockets, and it's very important to emphasize that they had different apogees. The very first one went to about 124 kilometers, somewhat lower than predicted, but it met our minimum. And then the second rocket went to 131. So now I'm going to show you some in situ data. Start with the density, which curiously is significantly different between the 2 events. We're just trying to understand that. You can see there was a sporadic E event on the second one, but basically we had this sort of shoulder or whatever. I've seen this in some Peru data before on the first event and different densities, but basically its daytime ionosphere is pretty well established. We then went to our magnetometer data. And the magnetometer data is where we spend almost all of our time because we measure the magnetic field. Of course, it's around 50,000 nanotesla. We have to subtract the model, come up with a little delta B, and convince people that delta B is significant. So in this case, we have the 3 components. This one, I left the spin mod in. We tried to, and this other rocket, I took it out. This is the presentation I have. And as you can see, there's this, and the delta B west, which will correspond to the meridional current. The delta B west, has these little sort of shoulders, that's what I call them, at around 110 kilometers up like that. Also something in the delta B north, a little bit. The red line is the average, and very little in the delta B up. So now we can just take the get current from the curl of B, assuming these are spatial changes with respect to the rocket motion. And oh my goodness, how did that happen? All right, You'll have to bend your heads, everyone. Okay. This is the profile, and you can see these are northward currents, the meridional current, and they're peaking at about 110 kilometers. Sorry about this, about 2 amps per kilometer squared. But in fact, I was so proud of this result because they both up leg and down leg show a reasonable current, strongest going meridionally, much weaker in the zonal direction. Might have that on some other slides, but we'll just see what we've got here. All right, so now we go to the other rocket, and here we see much larger changes in delta B west, much larger. Okay, here we've averaged some of the spin, and some structure in the delta B north we're trying to understand, but basically much stronger. You can see here, this is sort of just where the 110 kilometers are for the up leg and down leg there. Oh, here, this one worked. All right, so here we have the up leg and down leg, and the very first result we have is the event that had the 50 nanotesla, which we just spent larger current. Is actually, the currents are about the same as before, they're just spread out over a much wider area. And in fact, so the integrated current is much larger, but it's not like at the equatorial electric jet where if the ground-based delta B the current is a function of the ground-based delta B as far as amplitude. In this case, we simply see a much broader current region. So here actually is the first rocket and the second rocket compared to each other, down leg, and again, this is the point I was just trying to make. The first rocket, here's a nice little current layer, 110 kilometers, there it is. Second rocket, not so much stronger, in fact, not even stronger, but just over a much wider area. And again, the ground-based magnetometer is going to give you the integrated current from above. It doesn't know. So that's the beauty of the rocket, by the way. So anyhow, so here we have this is one of our first results. Now, let's go back to this, though. Okay, this is just what I was telling you. The second event, much stronger. But again, if you integrate the current, you get it actually agrees with this 50 nanotesla. Moving on, we have our electric fields, which actually basically show very weak electric fields above 110 kilometers. I don't have this versus altitude, but really 0.5 millivolt per meter or even smaller for the first rocket and the second rocket. And you see it, well, wait a minute, what is it going here? Well, this is down below 100, where there's very interesting physics about, in the mesosphere, upper mesosphere, about are there large electric fields, and because you're not having a lot of plasma there, the neutrals are really taking over. But basically, in the Dynamo region, the fields are very weak. So now we can solve for the Dynamo equation, and we do that here. I don't have the winds yet from Jim. He's going to be showing those later. We're talking about them at least. But I just say we put in all our measurements, and here we can put in what would the predicted winds be. So here's the currents I just showed you. This is down leg. Here's the current from the first event, the current from the second event, much sort of broader in altitude. And as expected, the winds here are actually be a northward wind and rather modest. And here a much larger wind, about 140 meters per second. But we're still working on this. It's very preliminary. Okay, now ICON. And then I'll wrap up. So with ICON, these are slides provided by Scott England. We had the two events. So I'll be showing July 7th, July 11th. Here was sort of the winds from where they came from ICON during the passes. This is where the IVM data mapped down. But the key part is we did this on purpose, was to launch when we were getting data sort of over wallops. And then here are the actual winds from the first launch. It's a little hard to show, but this is like the 3 orbits, and the one closest to the launch was with the star. And you can see ICON did measure a northward wind. It should really put a dotted line here at 0. So it's actually not that. It's really above 120, much more of a equatorward wind. But nevertheless, here they are, and then the zonal winds are shown here. I'm going to take this opportunity. I really should have had a separate slide on this to just say the time GCM predictions were about the same for both events. You know, and this is the meridional and zonal winds from time GCM. You can see July 7th and 11th sort of lie right on top of them. Both predicted a northward wind that was modest, but our results are sort of suggesting that the winds on the second day were much larger. Here they are from ICON on that second day. And now the Icon does see larger winds, but not significantly larger. So we're still working on this with our Icon colleagues. They also see stronger westward winds here. And so we're trying to understand that. Again, we're sort of in the throes of this analysis with the Icon data. But nevertheless, we have good Icon data for the two events on multiple orbits. Now those little stars, oops. How do I go back? Okay. Yeah. Okay, here Scott has provided winds versus longitude for each of the passes that was closest to the rocket launch. So here for the July 7th, you can see that the northward wind was actually higher in altitude, actually stronger zonal, whereas for our big event, July 11th, we had the winds were lower in altitude. I think Tom was talking about this. So just that change, I think, is the most significant, because remember, the Hall mobilities and Pedersen mobilities change significantly with altitude. So we're looking to that as sort of the key to what's going on. Again, Wallop's longitude is about 285, right in the middle. Okay, so again, this is sort of our question: why was the daytime dynamo so strong on July 11th? And if you just look at it, here's two, and you can do this just with ground-based and Icon. You don't need the rockets. There's very strong currents. What was going on? And of course, we look to the winds for the answer, but we don't have that nailed down yet. So to summarize, we have comprehensive measurements. We see the peak currents near 110. They do not increase linearly when the ground-based mag increases, but the integrated currents that we measure are in agreement with the ground-based ones. Electric fields were very weak, so there wasn't any big electric field that might have explained that 50 nanotesla ground-based thing, because the electric field, of course, will drive a current. That's not the case. The dynamo equation does predict a northward wind. That's much stronger in the second case. Icon winds were different, but it's the altitude variations that we think is so important to understanding what's going on. And finally, the model does not predict a significant significant increase, or the differences between the two events. So I'll stop there. Thank you. Hard to see with these lights. Are there any questions? Are there any questions from the audience first? If not, I'll read these. Oh, I'm sorry. Go ahead, please. It's very hard to see with the light, so I need help from the organizer.
I have a question about the Qian simulation.
Yeah.
So do you have any idea about the lower boundary you used in that simulations?
Oh, that's a great question. I don't. I have to get you that. Those particular curves Scott ran, we could run it also at Goddard, sorry.
Okay, thank you.
I don't know. Oh, hi, Tom. Great.
So I really love seeing these new data. Your statement at the start was the conductivity profiles are super important for what you're doing, but I don't think I saw a plot of the conductivities. Or how are you?
Just the plasma density.
Yeah, but
I didn't measure, right. We did not, we had to use a model for the mobilities. Although Jim, I know Jim measured the neutral density and things like that, but we haven't folded that in yet.
So I guess my question is, do you think could have been a large variation in the conductivities at all, or is this part of the puzzle?
Okay, that's a great question. Okay. I actually think, and I didn't emphasize this, because we know to begin with the plasma density was different, just even without looking at the mobilities. But yeah, that could be it. Why was it broader? And it could just be the mobilities, which of course is the conductivity.
Okay.
Yeah, I love that solution. Or that suggestion. Okay, why don't I read these, unless there's a hand up? Okay.
I don't think all of them relate to this.
All right, thank you. Yeah.
Thank you.
Hi, everybody. It's functionally impossible to follow Rob, so I'm not going to even try and switch subject. Hang on a second. I'm going to see if I can share from here. Okay. works. All right. And then let's see if this works. Look at that. Can I actually wave my pointer? Okay, let me just, there we go. Hi, everybody. It's very nice to be here in person with everybody. When Katelynn contacted me and wanted me to talk about some conjunction experiments we've been doing between Icon and Millstone Hill, and I'm just going to do this as a bit of a looking at how the sausage is made for some of these kind of things and encourage you all to make your own requests for coordinated observations like this. And so maybe as the takeaway, you might understand a little bit more about what this involved. The short answer is it is not happening ad hoc. You do need to sort of put the effort into it, but I think you're going to see that there are potentials for discovery science if you do that, beyond whatever the Cal-Val particular goal is here. So a lot of what I'm presenting here from Liège in Belgium has a very nice paper which I in Space Science Reviews, at least I hope it's coming out, it's in the review process. I acknowledge Miguel Urco at Illinois for looking at some of the FUV data, and of course the entire ICON team, especially Steve Mendy and Scott England, who really were the people that you'll see that started all of this. So I am, not an optical person, I am a radar person, but if you go look at the Space Science Reviews articles, really what we're trying to do here is do a comparison with the ICON EUV and FUV instruments. So these are, of course, remote sensing instruments. And EUV, as you see in the top two pictures here, is looking at two different sources, 61 nanometers and 83 nanometers. But the idea is to retrieve the O+ profiles, which in this, for example, are these two red and blue curves for two different, for example, examples. And so for what I'm going to be talking about here, we're just going to focus on daytime measurements, since it's EUV, of the F2 peak parameters, which is something that I happen to measure reasonably well from a place like Millstone Hill. At nighttime, the FUV instrument kicks in, and that's measuring a couple of different emissions. And I'll mention briefly that that has assumptions about photoelectrons, and it turns out that I think there's a discovery opportunity in there, not that I have had the time to do the analysis yet. So for FUV, I'm going to focus on nighttime F region for that. And so, you've got ICON, for example, for FUV, it's looking, of course, across here and kind of looking at tangent altitudes right here. For the EUV, of course, similar sorts of things. And so this is really concentrating on F2 peak somewhere in the 300-kilometer range. Obviously, in doing this work about, hey, let's put a solid floor under EUV and FUV, I know the ICON team, of course, wants to compare for different data sources. This is from Gilles' paper, the one that's in review right now. He selected, in fact, a lot of cosmic 2 data because that, of course, those occultation profiles are available all the time. Ionosphere, he selected limited periods. Of course, ionospheres run all the time, but for his particular study. But Millstone, for example, which you see right here, does not run all the time. Sadly, I do not have the resources to do that. The aggregate of all of these data sources is, of course, much, much better than any one source. But for an instrument that doesn't run all the time, you need coordination. And you still want to use sort of the collection of all of these data to try to figure out not only how the instrument is doing, but to figure out whether there's other science that can be done. But my point is that for things that are running episodically, it's not that you shouldn't use them, and in fact, the radar is very powerful for that. You just have to coordinate. And so, just as a reminder for any students in the room, this is the Millstone Hill Geospace facility, which is run by the National Science Foundation. And we do a number of things. We run the Madden-Julian distributed database, which is where a lot of ground-based data gets deposited. We run TEC processing, global maps of total electron content as an integrated quantity. But what I'm going to be talking about, of course, is the left-hand side, which is Millstone Hill. And that's an incoherent scatter radar, and it has a very wide field of view. You can see this little blue circle here at 500 kilometers altitude, which it turns out that because ICON, of course, does not go up to the latitude of Millstone Hill, but it is looking north at times, we can use this profitably. And you can see, by the way, we run 1,250 hours a year. And if you know how many hours there are in a year, there's 8,000 plus hours in a year. So this is another reason why one has to coordinate. And I'm going to put something in the upper left-hand corner that I want to emphasize. NSF is not NASA. So you need to have interagency cooperation for the best science to come out, and I think that is something we ought to pay attention to as we go along with missions like GOLD and ICON, and then upcoming GDC and Dynamic, and those sorts of things. Again, an incoherent scatter radar, because it's a complicated instrument, however, it has a lot of capabilities. In particular, because the weak nature of the scatter, one can get full altitude profiles well into the top side of key parameters, as you see up here, like electron density, electron temperature. I'm not even going to be talking about plasma temperatures, and of course, there's also line of sight velocities. We really have sort of two modes that we measure in. For these full altitude profiles, we're using an ionacoustic mode, which is this funny little double-humped spectrum over here, which has, from an uncertainty point of view, 5 to 10% parameter uncertainty, depending on time of day and conditions. But it turns out that within the last decade, we've also begun routinely measuring something else, which is an even weaker scatter from Langmuir mode. So this is basically the fundamental plasma oscillation that is going on in the ionosphere, and that's 1% uncertainty, just on electron density in this case. And so one of the things I'm going to show you in this talk is those little two arrows, and if you have really good eyes, you might be able to see them. Those little bright spots are basically the F2 peak. And because you're measuring a frequency and you're not measuring a shape of a spectrum, you can nail this down to less than 1% uncertainty. So boy, for things like comparing instruments, that's really nice. Again, if you can get the instrument turned on at the right time. So how did this happen? Well, it turned out that the email you see on the left-hand side is how it happened. Steve Mendy wrote me and said, when we're at the sort of most poleward point of our orbit looking north, we should be able to get really good limb views. How do we make this overflight happen? So this wasn't a formal process. This was just interested scientists saying, could you do something? And then a loop started happening between Steve and Scott and Miguel Urco later in Illinois, who already knew how to pull incoherent scatter data and analyzing it, going through me, and then I, of course, had to consult the people who are the scientists who are also in our facility, like Shenrong Zhang, and Larissa Koncharenko, and Urcha Ah, and the rest of the Millstone Hill radar team who helped me figure out, for a flexible instrument that can operate in many different modes, what was the most appropriate thing here. And I counted. We had 24 email threads. We had about 100 messages, 90 to 100 messages going back and forth, just getting some of this set up. So it was a collaborative group effort, but it does not happen by accident. It does take time and resources. That's one thing for the community to remember, is that the best science comes along with a lot of interaction. So the first thing to define was what? And I think that Rob showed a little picture here. This, for example, is one of the ICON predictions. And if you can see this blue line here, the idea was that when ICON was at the top of its excursion in latitude, and when it was pointing north, it would be able to look over Millstone Hill, and that's this little picture on the left-hand side. This particular line, which is a little hard to see here, is the tangent height from ICON pointing to the north, in this case. So for example, for EUV comparisons, if we measured not only upwards, we get a vertical profile, we could get a point where ICON and Millstone Hill were looking at the same spot, and we could say, okay, what does the near F2 peak parameters look like there? Now, I've already mentioned the radar runs in a lot of different modes, and we don't like to do one-off experiments, just turning on the radar for 10 minutes to observe one thing and turning it off, that's not that useful. You're missing a whole lot of the context. You're missing most of the multi-scale and the variability. So what we always do is work with people who want to do this, and we try to make sure that the experiment is useful for more than one thing. So I said, well, maybe I don't just want to measure vertically. I also want to use our steerable and measure up the magnetic field line. So I'm measuring, for example, parallel velocities as well as vertical. So later, it hasn't been done yet, you could compare with MIGHTY, because I can look at the diffusion velocity by comparing those two, because the beams are fairly close together. It's a high, this is the dip angle at Millstone these days. You can also then use this data outside of what I'm talking about and look at regional TID and variability and gradients, because these two beams, you get you've got 2-point measurements. You can watch things going through the beam. You can look at coherence. And it's also good, for example, I could give this to Shenrong and say, please put this in your bin for long-term trends in climatology. So the nice thing is, when you're doing this kind of stuff, if you organize it right, not only the satellite instrument, but the ground-based instrument can use this stuff for more than one purpose, which is very attractive. And part of our mandate as a facility is to help the community do the best science it can, not only for one, but for many different things. So we did that. Here we go. Then the question was when. And so I had these little planning charts, which it's probably hard for you to see, but the point is that there's all of these colored stars, either red or green or blue. The red is when the conjunction point between the limb-looking EUV instrument and Millstone were within 100 kilometers of one another, and then, 200 and 300. So some conjunctions were better than other ones, but you can see the gradual orbit precession here. This is the daytime particular times, and you can see the orbit coming through daytime and then coming back again, and you can see it, of course, precessing backwards in universal time. So this is for EUV comparisons. On the right-hand side is a little more blown up. That was nighttime conjunctions. And so if you pay attention to sunset and sunrise, you can figure out what the best times are to do this stuff, and because of the precession rate, it's, somebody waving at me in the back there? Hello? When we schedule these things, we don't schedule it in just single events. We just basically do them in campaign blocks. So we try to defend an interval that we're going to do as many of these conjunctions as we can, and then we try to repeat that compared to the conjunction sort of tables. So here's an example. I'm not showing the icon EUV data, I'm just showing Millstone Hill here. The right-hand side is a plot of altitude versus time, and the black line right there happens to be when the conjunction happened. This is a log scale of electron density, and this is our vertical beam. And if you subtract, so this is the ion line. This is the stuff that's got 5 to 10% of uncertainty. It's important because you can see the context. You can see what's happening up in the top side and the lower F region. And if you have good eyes, you will notice that that is not a smooth profile. This is borne out by the right-hand side, which is that plasma line measurement. So the right-hand side is only the F2 peak. That has error bars on it. And the line here is when ICON came by and made that conjunctive measurement. Did it right in the middle of mid-latitude variability. These are garden variety TIDs that occur at mid-latitudes almost every day, 10 to 20% electron density variability. So that's very important to understand, and that means that after you've through doing this, you can go back and take the EUV data, which has different coverage than the Millstone data, and you can start doing TID investigations for it. So already by doing this, you realize that there's another set of analysis you can do on TIDs, just borne out by trying to make this measurement. So that's just an example of one of the experiments. And this is what Gilles came up for statistical results. Now there's a good number of experiments in here, and it's a little hard to see the details, but on the left-hand side is NMF2. So that is the F2 peak, electron density peak from ICON, where we compare EUV and Millstone Hill. 0% is right over here. So you will notice that there's a lot of variability. It's definitely non-Gaussian, but the NMF2 difference was 50% lower in EUV than it is Millstone Hill. And it turns out that's roughly consistent with the other larger statistical comparisons between ionosons and the Cosmic 2, which again you can find in his paper. But HMF2, it agreed within the uncertainty. The best I'm able to measure HMF2, statistically, there was a pretty good result, except for these blue things, which was November 2020, when somehow the retrieval was way off, and I think that's being worked on. So the point is, you get a statistical result by doing this, of course, a bunch of times, but there's also variability in here, which you can investigate further. So this is like any discovery science. Things keep popping out, much like what Rob talked about. Oh, we don't understand this. Let's spend some time investigating that further. All of this started with, let's do some conjunction experiments. Now, I'll finish up by talking about FUV. So this is all generated by Miguel. FUV did really well. And it turned out that as Tom Emmel mentioned, that the ICON instrument goes through various versions. And the latest version for FUV, which is version 5, what you see here this is the 135.6 nanometer brightness. And the line in there is what Millstone Hill saw for electron density converted to brightness. The better one maybe is to look like this, so that the ICON retrieval of electron density would be these solid lines, and the ones in the blue dots are Millstone Hill. They agree within 10% difference. So the FUV instrument is doing really well here. So this is with the version 5 correction. If you went and looked at the version 4, there were more issues with the normalization of this curve, but the team has cycled through to do some really, really nice alignment here. And then statistically, there are 38 conjunctions here from August 2021 that you can see. And this, for example, is Millstone Hill NMF2, and this is Icon NMF2. Same way for HMF2 and Icon's HMF2. And if you look at this, this again statistically agrees with the other profile I just showed you. But notice what's in the purple, or the magenta, I guess. We couldn't do this in February 2022 because there was a lot of conjugate photoelectrons at nighttime from the opposite hemisphere, right? It was summer in the southern hemisphere. And so even though it was locally dark, there was extra photons coming in from impacts of conjugate photoelectrons. And we just didn't do the comparison, but that's a science opportunity. If you can forward joint model these things together, you can start figuring out something about the spatiotemporal behavior of photoelectrons, which is very important for people doing for example, energetics. And by the way, I have a radar that measures plasma temperature, which was interesting for energetics. You could even try to pull out some things about the superthermal photoelectron spectrum, that plasma line measurement. If you make it in just the right way, you might be able to tell some things about superthermal photoelectrons. That's quite a stretch goal. That's going to require almost a dedicated graduate student to do it. So if someone has time, there is more discovery to be had here. Again, all emerging out of just a coordinated effort. But mid-latitude physics can surprise you. So what I'm going to leave you here is, this is a particular experiment we did back in August 2021, and that is the electron density behavior in mid-latitudes at nighttime. The line is where Icon came through. There's a well-known summertime electron density evening enhancement. It's actually, the density goes up after the sun goes down for you students in the room, and it has to do with a combination of neutral and ion seasonal factors. And then there's this abrupt lifting of the F peak for about an hour or two, and then it goes back down. There is a repeatable electric field signature that Shunrong and I haven't completely traced down. There's yet another discovery experiment in there to try to work out mid-latitude physics there. So my point is, none of this is in the International Reference Ionosphere, but it's there if you make measurements for more than one thing and compare them. So that's just another thing to remember, is that mid-latitude has a lot of variability, and you can pull it out from experiments that were designed really primarily for something else. So I'm just going to end by saying that planning this stuff early, for example, in future missions within CalVal opportunities, would really help. The joint resulting discovery science that flies out from this, people to do the science analysis are very important. We have limited resources from our wonderful scientists at Millstone, and it would be really great to have other people doing that. And I mentioned interagency cooperation before, and I also want to mention that discovery helps fight the trend for a student that says, oh, this is a calibration and validation effort. How am I going to get something out of that for my PhD? Well, a lot of the stuff I've shown you, if you follow those threads, there's lots of good information there for a PhD, I think. I'm just going to end by saying this was all because of wonderful and frequent and dedicated discussions in working groups, and that's really what you need to do to maximize this kind of joint work. And so I encourage this community, as we're getting back from the pandemic and being in the same room and actually enjoying talking to one another, just chat with people in the hallway that you know have an instrument and see what ideas emerge. And we don't know where this is going to lead, but there's always going to be something interesting in what you're measuring. So I'll end there. And Rob is right, I can't see any of you.
Thank you. Yeah, thank you, Phil. I was really intrigued by your comparison, the statistical comparison between the Millstone Hill results and Icon. So this deviation of a Gaussian, so the secondary peak you had there. So I mean, that clearly shows how important it is to look into the same volume from different perspectives there. Yeah. So what is your best guess what the physical reason for that is? Is that looking into different scales because you sample different air volumes, or any idea?
Yeah, I think that's also, and somebody on Icon EUV, for example, or Retrieval could comment on this more often too, is that you always have to separate out the potential difficulty with a subset of the retrievals themselves, so the instrument versus the geophysics. If some of what you're seeing there in terms of variability, okay, yeah, the bias may be a case of we have a constant off or some assumption is a little wrong, but I think the variability maybe, the best we were doing was getting, our best conjunction was getting within 100 kilometers, okay, and I mean, that was good. We all know that there are many, many different scales in the ionosphere, and I will bet you that there are scales at tens of kilometers. We've seen them in the plasma line data, which has a lot of short scale variations. And you may be just seeing another component of variability in the upper atmosphere that two instruments with different perspectives, right? EUV does things that the radar cannot do, and vice versa. I think if you're trying to put them together, you start to get fuel for trying to look at the spectrum of variability. So I think there's some of that buried in there after we work out the instrumental details. Anybody else? Oh, yeah.
Hi, this is such great science. It's so exciting to see these conjunctions happening with the ISR. What I was wondering about with the photoelectron problem, this is more for the FUV. Retrievals are not reliable because of that?
My understanding from looking at Gilles' earlier paper in one of those is that there's extra scatter that's occurring because of the impacts of these photoelectrons, all right, which are not local. They're coming from the other end of the field line. And the retrieval algorithm may not necessarily, may be assigning some of those extra photons as to extra density when in fact it's these other impacts. But as you know, photoelectrons have a spectrum, okay, especially superthermals. And one of the great unsolved problems in this is what is the spectrum of those superthermals and how do they affect, for example, the thermal behavior? So in some sense, the fact that there's this instrumental discrepancy then leads you down the path into something else from a science point of view, which says, how do we look at the thermodynamics of what's going on? And the thing that I can mention that is vastly underutilized in the community is that the incoherent scatter radar has direct plasma temperature measurements. Because of the scattering physics, we literally directly measure electron and ion temperature. And connecting that into the photoelectron spectrum, Roger Varney did some work with SAMI-2. There's a PE photoelectron version. But getting more modeling and more data happening there, I think, is very important to understand the thermodynamics, which then affects what the density is doing, and then affects the variability. So I think there's the threads that lead you to another area that I think would be very interesting for people younger in their career to pursue.
And are there, just to follow up, are there any supporting optical instruments at Millstone Hill that can pick up the airglow emissions that result from photoelectron impact?
Yeah, we've had a patrol instrument that does both red and green line for decades, and that's run by, it's run right on site. So we have a co-located FPI, we have all-sky cameras. It's mid-latitudes, so there's sadly clouds in New England sometimes, but certainly for everything but a couple of days, on either side of full moon, there are also direct red and green line measurements, which, for example, you can use to measure winds and temperature. So yeah, there's a whole nother set of data I didn't even talk about. That doesn't have to be scheduled. That's just patrol mode. That occurs all the time. So once again, it's a matter of figuring out how to optimally combine all these things and do sensor fusion.
Thank you.
Oh, yeah, Richard, please. Yeah. Right, and so yeah, Richard, for those people online, is mentioning that Gold has also done work on conjugate photoelectrons. We know they're there. We know they have their own variability. And I think we don't very understand a lot of those details quite yet because we're just beginning to collect this data. So again, another nice opportunity.
Okay, good morning. Like to continue basically where Rob started, and here's our author list. My students plus Rob and Scott at Virginia Tech. So like to go briefly over the Dynamo 2 rocket experiment. and talk about the neutral atmosphere instrumentation, the data we received, some of the analysis that we've been done, and the progress and results that we have. So this is the overview. Since Rob did such a great and comprehensive introduction, I really won't talk about it here, but basically the rocket instrumentation consisted of measurements to measure electrodynamics, plasma, and neutrals. And so I'm going to do an overview of that third bullet there. So the neutral atmosphere instrumentation we had on the rocket we had several ionization gauges, they're pressure sensors, that were on the spinning main payload. And we're able to use the spin and the signal modulation that we get from the spin to determine atmospheric parameters other than just temperature and density, namely winds. And so that's one technique that we have to attack the neutral atmosphere. The other thing that we have, as Rob said, is really our first time at flying this in a three-axis stabilized mode, which is our winds instrument. So we have actually 3 instruments to measure the winds. The winds cross-track, which measures the direction, the components of wind across the track of the motion, and the in-track that measures the third component that's along the line of travel of the rocket. And we also had something called the winds imaging instrument. That was more of a technical test because we really didn't get to altitudes or speeds where that would work too well scientifically, but just as a technical test of that process. And then finally, we also had some extra ionization gauges to basically baseline what's going on with the neutral winds measurements on this thing. So let's see, is there a pointer that's on here? Oh, it's in the middle. So this is that payload. So this is that little winds imaging sensor, and this is the in-track winds instrument. Has a small aperture. This is the winds cross-track instrument, which I'll focus most on here. This is an ion mass spectrometer that we flew, and then on here one of the ionization gauges that was on the end. This is the second one right here, and then there's a third one down at the end of the payload here. So that's the thing that we're going to be looking at. So I'm going to start with the IGs. I think that's what people are most familiar with. And so the spinning components consisted of these 4 gauges, and once they're opened up to space, they measure the amount of gas that's rammed into them. And as it spins, we see the signals that are created by that spin, and we're able to analyze those to get the winds and also the temperature. The 3-axis component consists of 3 evolved winds instruments. I call that evolved because we've changed them quite a bit since we flew them last in the Auroral Jet campaign back in 2017. And so those are the ones. So first looking at the spinning IGs, this is an example of the data that we received from one of the launches, just one of the sensors. So black is up leg, red is down leg, and basically where we see these peaks, those are going to help us determine what the winds are. This is a little schematic of how that works. Essentially, we're triangulating in velocity space, and so we need to assume that the up leg winds and the down leg winds are very similar. They differ negligibly, and that they're also vertical winds are negligible. Both of those are pretty reasonable assumptions in this particular experiment. So basically on the up leg, we find with the black ones, we find a plane where the winds must lie within a given altitude, and then on the down leg, we find another plane. And if these planes intersect well, then we can find a locus of intersection here, and determining that the winds are vertical winds are 0 determines that position right there. And so I should say that's based on a technique that apparently was done by Butko back in the 1970s. So this is what we retrieved from the spinning IGs for the first mission, the 7th of July mission. And so you see our density here compared to MSIS in blue. And we haven't plumbed this, as Rob said, for what's going on with the conductivities. Certainly something that we should be engaging in. Here's the temperature profile, and this includes both the one from ICON in red and the MSIS, as well as our measurement here. So we are agreeing pretty well with ICON in this case, and it looks like there's a little bit of enhancement, several, maybe almost 100 Kelvin in enhancement over what we see in MSIS. So there's something going on here, some energy being absorbed by the gas and increasing the scale height. We get the zonal and meridional winds, and here the icon is again in red, and we're seeing kind of the same trend in the data, but we see much stronger winds, and same thing for the meridional. Now we don't consider this a complete work because we have noticed that there's a lot of coning in this measurement, and the previous slide, it really requires the spin plane to really be a plane. And so there's going to be some, I think, adjustments of these winds due to figuring out what's going on with the coning. And then we did calculate the U cross B term, and you see that it's more than just the 1 or 2 millivolts per meter that Rob had. So we're seeing that, it's really being driven by the winds. There's sort of 10 millivolts per meter here. Even if the winds were to decrease a little bit, we would still get strong terms over here. For the second shot, we have a similar sort of thing. Our agreement now is not quite as good with ICON. Sometimes it agrees more with ICON, and sometimes it agrees more with MSIS, so not quite sure what's going on. This particular piece of the zonal wind we're quite concerned about. It seems to be probably quite a bit off. And so again, we need to look at this more with our attitude solutions and the coning that was present. So now I'm going to move on to the new stuff with the Dynamo 2 instruments, and just a brief introduction of how that works. Basically, gas is rammed in here to what we call the outer aperture. That's this green piece here. So this instrument is kind of flying at you. And then there's a blade inside. That's this thing. It's actually a 4-bladed vane that goes around at 2 hertz. And it modulates the gas that comes into this accommodation chamber, and then is measured by this ionization gauge here. And so pretty simple concept, just simple modulation of the gas going in, and we get a signal that's supposed to look something like this, and from the flight data, we get a signal that looks like that. So we consider that to be kind of a success. We also have this in-track instrument, also provides information on in-track winds and the temperature. It works by chopping the gas flow into small puffs with this chopper wheel that's here, and those are then timed as they drift to be detected here in the back of the instrument. And that time of flight then gives us an indication of the gas speed there. And I'm not going to talk about that much today. We had some unexpected, it didn't perform nearly as well as it did in the calibrations, and we think we understand why that we had a very high background rate here. And so we're looking at some modifications of this, learn some lessons here. And Diana Swanson's poster covers some of this in the Wednesday poster session. So going to the analysis of the WCT and how we do that is basically we calculate the response to simulated beams that have a wide variety of temperatures and velocities in both in-track and cross-track, and we get these sort of shapes here. And so this is meant to be 3 different cross-track speeds here. That's what these three bumps are, and then there's 3 colors in each. Those are each 3 different temperatures. So you see we have response to both direction and temperature here. This one is more of the same data, just plotted again. I'm not going to take the time to go and explain that. We have done what we call a retrieval through this. We make a catalog of this because this takes a while to compute all these curves. And so we make a catalog, and then we put some randomized data into it and see what we come back with, and we see that we get some very narrow error distribution. So it looks like this at least this portion of the mechanism of the analysis works pretty well. So that's the gas that flows into the instrument. The thing is that we also have this accommodation chamber on it, and that actually changes things a fair amount. And so we analyze that by looking at the change in density is just the amount of gas going in, that's modulated amount here, minus the amount that's going out just due to the thermal exhaust of the instrument here. And so, very simple thing. This tau CH is what we call the time constant of the chamber, and that's given by this simple expression here, which is just its volume divided by the aperture area divided by the most probable velocity in the chamber. And so this is kind of interesting because what this says is if we can measure tau, we can get a measure on the velocity in the chamber. In turn, that gives us a handle on what the mass of the particles are in the chamber. So we have sort of a poor man's mass instrument here too, in principle. So since those previous curves match Gaussians pretty well, we just model our signal, our modulated signal input with this, and we can solve in closed form what we should get as a equation that we need to analyze this against. Here, lambda is an initial condition, and we use this to fit the data that's returned by the WIT sensors. The WCT sensors. And so this is an example of one of the sensors in flight, and you see the pressure starts high and goes low and then goes high again due to the transition through the atmosphere. These noisy places are where we reoriented. We had to reorient the payload several times to stay in the RAM, and that's the ACS, combination of the ACS gas and moving the payload a little bit. So we analyze these curves. So this is one such curve, as you saw before, and the width of the valley gives the thermal spread, and then the position that it falls on the axis here is the position. So this is one of the fits, and the black here is the data, and the red is the fit. And because you can't see too much black around the red, that means we have a good fit. So the analysis I'm going to talk here is sort of the way that we've been going about things, but I'll say that Lance Davis is also working on an alternative approach to analyze these data, and he'll be talking about that as poster on Wednesday. He's using, I guess, more modern things, machine learning and those sorts of things. We'll see how that works on Wednesday. Anyway, here's the analysis. So these are the data now from one sensor, up leg and then down leg, and these have all been normalized so that each peak, basically the altitude is normalized out of here. So it's just normalized to the peak there. So what we see is this valley here, that's our wind measurement, and then the width is our temperature measurement. Here's our ACS reorientation, and then we measure more on the up leg, and then down leg, sort of similar kinds of things. So going through this, these are the results that we get at this point, and so these are the retrievals. So this is the key down here. So on the up leg, we have black and red. So black is the zonal, and red is the meridional. And then on the down leg, we have green and blue. So if the winds are the same going up as they are going down, we would expect the green and the black to lie on each other and the red and the blue to lie on each other, which they kind of do in this sort of region above 120 kilometers. Down here, the agreement is not so good, but I'll say that what happened here is we had a little problem with the attitude not being terribly stable, because we're coming into heavier or thicker and thicker atmosphere, and it actually exerted a torque on the payload. And we haven't figured out really how to address that within our fits. And so we're still working that. Probably have to add a couple more terms to what we're already fitting. The temperature is also, there's some degree up here of reality. It still looks pretty far off. I should say the pink line is EMSIS. And so we're kind of off by a factor, but at least it's nice and stable, and we don't see all sorts of crazy excursions and so on. And again, below 120, we're having trouble with our attitude. So that's for the second mission, the one on July 11th. The results from July 7th are also in progress. They're a little bit behind these, but they're showing the same sort of thing. So these are my conclusions. So basically, significant progress has been made in understanding the neutral atmosphere during the Dynamo 2 missions. And the density and temperature been measured in 3 different ways. We have the spinning IG, the cross-track wind sensor, and then ICON. And so the agreement among the 3 methods is promising, still needs more work. I'd say we're kind of at the 50% level on the agreement there. And of course, the work on the WCT data is most urgent. And so we're looking at better applications of initial conditions in the fits. That by doing that, we can reduce the free parameter space to an appropriate value. So 6 parameters instead of 5. And so right now that lambda is allowed to be a free parameter when really it's not. And it kind of hurts the fits a bit. And so we're going to fix that up. And the other thing is that we've got kind of a simple approach to the changing atmospheric density as we go up and down, and we want to do something a little more sophisticated. But so the bottom line is the coordinated measurements that we've talked about with ICON and the Dynamo 2 are key to developing more high confidence results. So I will stop there. Okay.
When you were comparing with INSIS for the winds, is there any a priori information in that with INSIS, or you showed the...
Okay, yeah, MSIS doesn't model the winds, so we were using the HWM there. And so I think that the level of HWM maybe shouldn't be expected to agree in detail at this sort of single experiment level. But we put it in there for completeness, yeah. Yeah, they're very strong. Okay, thank you.
Okay, so good morning, everybody. So Katie asked me to talk a little bit about Cosmic 2 data in the session here. And so those of you who know me know my main scientific interest is looking into what does lower atmospheric weather do to the upper atmosphere. And for that, I'm trying to make a case that actually Cosmic 2 data are really an absolutely great data product to work with. In particular, if you're interested in global scale, so for people like me. And how do I... Okay, so finally, so what I want to do in the beginning is, for those of you who are not so familiar with the Cosmic 2 data, to give you a little bit of an introduction about the electron density, in particular the GIS data product. Then talk about the results during the 2020-21 SSW event. And finally, talk a little bit about ongoing work on the Madden-Julian oscillation. So, Cosmic 2, so this is a 6-satellite constellation mission launched in 2019 in the summer. Essentially, the Cosmic satellites have an IVM instrument on board and radio occultation measurements, so GPS measurements. And the important thing for the work I'm interested in, global observations and global diagnostics, tidal diagnostics, which really depends on having a local time coverage. And so the satellites are now in their final orbit configuration. So that means they are about 530 kilometers in altitude. And they have a 60-degree longitude separation. So that means automatically a very good local time coverage. So the GIS data product, so GIS stands, if I remember correctly, for Global Ionospheric Specifications. So these are actually electron density profiles. They come from the radio occultation measurements, but these are not just the observations, but these are actually assimilated data. So that's a Gauss-Markov Kalman filter. And what people in Taiwan do, so I'm using the data here from NCKU. So they use the cosmic 2 radio occultation measurement, so that's low inclination data up to 24 degrees latitude, and for higher latitudes, they add ground-based GPS data and then basically put that into an assimilation system. And as a result, what you get are hourly profiles, pole to pole, on a regular grid, longitude, latitude grid, and every 20 kilometers. So in the end, it's almost like you're getting model data, but very close to the observations. Okay, so that's also something that's very easy to analyze. So this is just some quick look data I pulled from the web page at NCKU. So on the left, you basically see one hemisphere with 1 hour time resolution here. So I plotted here just arbitrary the 1st of July 2020, so to give you an idea about the time resolution, and what's color-coded there is TEC. And here on the right-hand side, that's the same day, but now as a function of latitude. Okay, so world map here, longitude, geomagnetic equator, and then color-coded at different altitudes, the electron densities from the GIS data product. And so basically, you have maps like that with 1 hour time resolution and every 20 kilometers in terms of an effective resolution. Okay. So what I'm interested in are tides, tides from the lower atmosphere and their effects. That means having this kind of global data set, so on a latitude, longitude grid, every 1 hour universal time, that makes it very straightforward to do tidal fits. So in the end, these are 2D Fourier decompositions into a zonal wave number. Okay, so what I'm plotting here, that's from 21. So these are at 15 degrees north, magnetic latitude, 300 kilometers, basically the signals of 2 very particular so-called non-migrating tides. So the specifics here are not so important. The point is we know from work over many, many years that these 2 tidal components here, these 2 tides, both diurnal tides, they really come from tropospheric weather systems, basically the distribution of convective systems at the low latitude. So what you basically see here is a result of tropospheric convection. And this is basically the same, but now at fixed 300 kilometer altitude as a function of magnetic latitude. Okay? And so this one here is scaled in relative amplitude, so relative to the zonal mean, to give you a kind of an idea how big actually these variations in the ionosphere are that come from the weather system. So you see it's on the order, give or take 20% from a single tidal component here. And keep in mind, when you do observations, you always see the superposed effects of all these different tidal waves, these tidal components there. So you have to add 20% here, 20% here, and all the other tidal components that are there. So we are really talking about quite substantial variations in time and space. So and here, that's a plot I did actually last week. So my apologies, that's in geographic coordinates here, but in magnetic coordinates it looks pretty similar. So that's basically the tidal spectrum for a single day. Okay, so what's plotted here is zonal wave number versus frequencies. So basically you see the mean here, the diurnal tide, a diurnal migrating tide, semi-diurnal migrating tide, and all the different non-migrating tidal signals. So for example, this blob here is basically what you see here. Okay, so you see there are many more wave components around, and they will all add up in terms of producing variability. And for for an aeronomer like me, who is really interested in understanding how tides change from one day to another. And that's really important because a lot of these tides really come from lower atmospheric weather. And I mean, we all know weather, it changes from one day to another. And in my view, really quantum leap forward is the Cosmic 2 capability to really provide global ionospheric data every hour with 1 hour time resolution. So that means I'm able, or we are able, to produce spectra like that every single day. And that's something so far we are not able to do in the neutral atmosphere. Okay, so there, with a single satellite, you simply can't do that. Okay, that's impossible. That's why we are really looking forward to constellations like GDC or Dynamic to produce something like that also in the neutral atmosphere. So this one here is now a time series of the semi-diurnal migrating tide. This one is now in magnetic coordinates, 20 degrees north, and I plotted 380 kilometers here, but it looks pretty much the same at other altitudes. And what you see here on the y-axis is the zonal wave number, time. This is amplitude here in percent, electron density variations. So the colored band here is the semi-diurnal migrating tide. Okay? And all the other wave numbers are non-migrating tides here. So that's in the northern hemisphere, northern crest, southern crest here. And so there are two things I want to emphasize here. So first thing is that we are talking about relative variations on the order of 30% or so. But you also see it can change from one day to another from 10% up to 40%. So we are really talking about a lot of variability. And secondly, you can see that here past day 360, so basically very early in January 21, we see a little bit of an enhancement here in terms of the magnitude of the tides. So this is a time period when we had a sudden stratospheric warming going on. I have actually another talk on Wednesday specifically focused on the sudden stratospheric warming in January 21, where I discussed that in the context of gold observations and icon winds in the E region. But what I want to emphasize here is basically this figure here. So what you see here is now magnetic latitude, okay, so time again, and now color-coded the amplitude of the migrating semi-diurnal tide here. So northern crest, that's what I just showed you as part of the spectrum, southern crest here. And if you look into the black curve here, so the black curve is the zonal mean, zonal wind at 60 degrees north at 10 hectopascals. So for those of you who are not so familiar with stratospheric warmings, that's a kind of measure people use to look into if a stratospheric warming happened or not. So stratospheric warming is basically a breakup of the polar vortex. Okay? And so if you have that, you change dramatically your zonal wind speeds. So the stratospheric warming basically happens if you go from eastward winds here to westward winds here in the stratosphere, in the polar stratosphere. And I mean, when I plotted that, and I mean, I actually produced this plot 2 weeks ago, and I was really stunned when I saw that. It's not only that you see a clear correspondence with enhanced tidal amplitudes here during the stratospheric warming. I mean, even if you look into the smaller wiggles here, you see how closely the ionospheric tides really follow the wind speeds 300 or 350 kilometers lower down in the polar atmosphere. And I mean, looking into this kind of close correspondence, that's a time correspondence, that's really only possible when we have the ability to diagnose tides from one day to another. So if you have a single satellite, we always have to average tidal diagnostics by a month or something like that. No way that we can actually look into this one here. And so this one here, perhaps more for the specialists. So these are the corresponding tidal phases here. If you look closely, you see a slight phase shift towards a little bit earlier local times in the electron density responses here. That's also what one would expect from a theoretical point of view. So a couple of hours towards earlier times here. And to move on to another coupling process with the lower atmosphere, now specifically with the troposphere. So what you see here is the so-called MJO, so that's the Madden-Julian oscillation. So the Madden-Julian oscillation is a tropospheric weather system. It's a recurring weather system global at low latitudes. And basically what it does, it changes cloud coverage and convective activity, rainfall rates at low latitudes every 30 to 60 days, give or take. So the Madden-Julian oscillation is known for a very long time. The climate and the weather forecast community really put a lot of effort into that because it's, for example, very important to predict the Indian monsoon, how the MJO really looks like. And so that's a kind of a standard way to analyze that. So you plot time of year versus longitude at low latitudes here. And what you see here is a modulation of convective rainfall. So basically a bandpass filtered 40 to 60 day rainfall rates as convective activity here. So you see enhancement and depletions. Everything goes a little bit that direction. And then from a NASA grant, we actually looked into how the tides respond to the Madden-Julian oscillation because convective activity and cloud coverage is an important source of the tides. And what you see here are SABRE results in the MLT region. Temperature tides basically analyzed the same way for the migrating diurnal tide and the non-migrating tides that comes from tropospheric convection. So that's work Komal did, my previous grad student. And so we have a decent understanding how to connect the tropospheric convection here with the tidal activity in the MLT region, or in other words, in the E region. And because the E region, the Dynamo region, is kind of driver for what we see in terms of tides in the F region. So I actually looked into, or started to look into the Cosmic 2 data. And what you see here are very initial or very first results. So that's actually, I just got a new LWS grant to really work that out, how this connection works. But I nevertheless want to show that. So what you see here are icon zonal winds at 100 kilometers and the equator. So zonal wave number versus period. So this is basically a 35-day average centered around the 1st of July. So you see diurnal migrating tide, semi-diurnal migrating tide, a bunch of non-migrating tides here. So very consistent here in the temperature data. And so the temperature are version 5 data and the zonal winds are still version 4 data, if you're interested in that. And this is a corresponding spectrum from Cosmic 2. Okay? So in electron density here, 20 north crest region, and that's only from a single day. Okay? So, and what I did was basically computing this kind of spectra for every day for the year 2020. And then I looked into what kind of variations do I really see in the tidal amplitudes themselves as an average over a year. So you can easily do that by simply running a Fourier spectrum of that. And that's what you see here. So that's basically the Fourier spectrum of the migrating diurnal tide. So basically this blob here, this blob, and this blob. And then for the whole year 2020. And color-coded the spectral power as a function of period. And so it's normalized in a way so you can, hopefully you can see this little dotted horizontal line. That's a 99% statistical significance level here. And you see, we see a 45-day period signal in the mighty green line data in the E region. Similar signal in the temperature data. We see the same periodicity in the cosmic data, 280 kilometers higher up. And the red curve here is the so-called MJO index. That's basically the convective activity, the variation of the convective activity at the low latitudes. And I mean, if you look into that, this is really a strong indication that by now we have the kind of data available to make a coherent case to follow this kind of weather variations, these recurring weather variations from the troposphere, convective activity, to the E region in the Icon tidal winds, and then connecting the whole processes through dynamo processes into the F region ionospheric tides. That's, of course, a very rough analysis here. So to really do that in a more coherent way, we have basically to redo analysis like this one here. But I mean, even a straightforward Fourier diagnostics shows very promising results. And so with that, I want to leave you with the conclusions. So perhaps the two basic messages here are that if you are interested in global scale variations in the ionosphere, planetary waves, tidal waves or so, the GISS data from Cosmic 2 are really a great data set. That's, I mean, very easy to analyze, high quality. So, I mean, there's really a lot of meat in that here. And in the spirit of this workshop here, the really, in my opinion, cool thing is that we now have, I mean, Cosmic 2 data in the ionosphere globally. We have the Icon data for the Dynamo studies. We can make coherent cases down to the tropospheric forcing. And as I will show on Wednesday, we have the gold data that basically complements the whole thing in terms of thermospheric composition and how, for example, diffusion adds to the whole picture here. Okay, thank you. Yes, I have. Can you show something? I don't have that as a slide here, but I mean, I did run the tidal diagnostics basically for 2020, 21, and 22 so far, and so I have the data, so I can show that to you. So you see the tides maximum change with yes. Yes.
All right. I was sort of stepping. Actually, Yuri Cherniak supposed to come here to give this talk and give you an update on Cosmic 2 mission status. And glad that Jens Oberheide is giving you a promotion for the Cosmic 2 data, usefulness of Cosmic 2 data. And so should acknowledge that the Cosmic 2 team has a lot of team members, and Young West is our PI now, with others, and a long list of people working very hard on this project. So, where's the pointer? I have a pointer here. Which one? So, figure out this one here. Nope. Here we go. So Cosmic 2 has 6 identical spacecrafts, and it has a few instruments. One is the IVM, and it's from UTD, identical to the Icon IVM instrument. And the main instrument for the Cosmic 2 is, of course, the GNSS receiver we call the TGRS, and it's a tri-band GNSS receiver, and it should be able to do GPS, GLONASS, and Galileo. Galileo is still not ready yet, and right now we have a GLONASS and the GPS, and it has 4 antennas, and this is a looking forward direction, moving forward direction. We have a pod antenna, which for orbital determination, and have this RO antenna. That is really the main focus of the mission for lower atmosphere bending angle detection, and has a array of small antennas to have focus beams into sampling lower atmosphere as low as possible. And also we have a beacon, tri-band beacons on the spacecraft. If you have a receiver on the ground, you can look at the scintillations of it. And it was launched on June 24th, 2019, and it was parked onto the high orbit of 700 some kilometers, and the first spacecraft was lowered down right away and to 500 some kilometers, and the other spacecraft gradually lowered down so that the spacecraft, 6 spacecraft have equal spacing in longitude, and so people like Jens Oberheide would be very happy. We have a more local time sampling instead of clustering together in the same location. So you have a more local time sampling on that. So it took a while for all the spacecraft to lower down to the lower orbit. And I should mention that the Cosmic 2 is a joint mission between Taiwan and the US. And here's a geometry of the spacecraft and sampling. We have 2 antennas of pod antennas, one looking forward, one looking backward, and 2 RO antennas, one looking backward, one looking forward. And so both 4 antennas and coming into the spacecraft from the GNSS receiver, and it has a limited number of channels in there. So it's how you allocate the resources of the receivers to sampling different things for the mission. And here's give you a favor of how many samples we could to make. For this is for the TEC occultations, and this is for GPS, and for each from different colors for different spacecraft, and we got like 4,000 something like that samples per day, and this is from GLONASS, and we got like 2,000 of it. And the brief time period we have more of them, but that was time how to allocate the channels. That's only limited number of channels how you allocate, and so. Right now we're stabilized, and so this is what we have. So 6,000 GPS occultations we got each day on that. And we spend a lot of time, because this is an operational mission, and we spend a lot of time to calibrate the instrument. First, we calibrate the TEC from GPS, and by comparing with a SWAN-B. And when the spacecraft of the SWAN-B and coincide with, not in collision, but very close to Cosmic 2, and we're looking at different GNSS receivers and trying to compare, looking for coincidence when they are very close to each other, and do comparison, with a pretty good comparison of the validated GPS. And with similar things we did with GLONASS. GLONASS is a new thing for us. Cosmic 1 doesn't have a GLONASS, so Cosmic, now we have GLONASS. And Nick Patatella, who you all know for modeling effort, for modeling specialties, and he has also spent a lot of time taking care to the modeling, to the data processing for the GLONASS, looking at the BCDs, all those things, and getting the TEC data out of that. And for this, we're looking at when the GLONASS spacecraft is in the same direction as the GPS spacecraft. So when the spacecraft looking in the same direction, both the GLONASS and the GPS, looking for coincidence and to compare the TEC data between the 2 clusters, and we got a pretty good agreement between the GLONASS and the GPS TECs, so that when you mix the data together, there's no offset between them. Of course, people do the comparison with the ground-based ionosons often, and this is we've done that as well, and good agreement obtained. And another new product from Cosmic 2 is geolocation of scintillations. And when the onboard S4 value exceed threshold values, and the spacecraft will download high-rate data from GLONASS and the GPS and the high-rate data. And based on backpropagation method, we can accurately determine where the scintillations come from. That is a huge advance compared to in the past. You look at S4 data and you're along the path, you don't know where that scintillation is coming from. It's not like you have a optical observation, you have a kernel, you have a weighted kernel, you can say that's in the tangent point, and tangent point usually is not that case. So backpropagation is a way to do that. And we did a comparison with a gold bubble. We come up with a logarithm to determine where the bubbles are and compare with the geolocations, which is in the green color circles here, and the spacecraft, for the spacecraft looking this direction, and we found the scintillations and propagating back to this place here. And we have two versions of it. One is from UCAR, developed by Sergei Sokolovsky, and another one's by BC, and they also have a propagation geolocation method to determine where the scintillations are. So we compare both of them with a goal. And we'll both obtain pretty good agreement set. Another thing we did is that the Cosmic 2 has an IVM instrument, and we validate the IVM density so far. And the way to validate that is that using the TGS TEC data and looking at the time that when the GNSS spacecraft is just right in front of the Cosmic 2 data or right behind you, and taking the differential TEC to obtain electron densities, on-orbit electron densities, and compare with the in-situ ion density measurement. And of course, that doesn't happen often, and only a few times during the day, and which is we plot here. They all seem to line up with the IVM instrument data pretty well. And we did some comparison with them, with IVM, and we did find some offset between the IVM and TGS observations, and we correct that. And not all the data are sort of uniform, and it would be good for, again, for people like in the Oberheide, so there's no offset in there. So in summary, let me see, where are we? So the instruments are all pretty healthy, and most of the data are available right now. Regarding the IVM, we have the densities available, all calibrated. We're still working on the IVM drift, so that data is going to be a while before we can put it in public use. So that's it. Any questions?
We have one quick question.
When is it expected that the Galileo RO data is going to be available?
Oh, I'll pass that question now. GPR is still working on it.
I want to thank all of our speakers for coming today. I also really want to tell the students how much we appreciate you guys being here for this workshop. We will reconvene, I think, at 1:30. In the meantime, this room is going to be used for the student luncheon. So if you're not part of the student luncheon, I think they want us to clear the room. But thank you again for attending.